Oh, it's recorded. Okay. So while maintaining the relationship of that components that is created with another software. Okay. So that is basically In-CAD technologies. And let's have a little bit a deep dive on it. Okay, so here you can see on the left, I have files, SolidWorks files, open up in SolidWorks, and then in Inventor on the right-hand side, I open up the same file. Okay, so I open it up in my Inventor. You can see that now it looks pretty much the same. Okay, and then the things that I can add, probably things like center point, or I want to add a new profile, I can do it as well. But in this case, I want to reuse this so-called part. I just added a center point for the holes. I can specify a new material if I want to. Okay, so in this case, I'm using the Inventor materials. I can also assign and create my own if I want to. I can color it accordingly if I want. And also, what we can do here, of course, I'll explain more on the workflow after this. So I need to from here, I can just process by putting in all the constraint needed, okay, to run this analysis. And then what we can do is I can just add loads. Okay, so if you want to run the analysis, of course, obviously you need to add loads, right? So added loads through edges. So basically from that SolidWorks parts, I can detect all the edges, all the spacing, face. Okay, I can just reuse it. Okay, apply a connectors. So in this case, so in a simulation study case, a connectors is something like something to replace your for example, a fastener. Okay, so probably that part or that area, that component there is positioned within a shaft, maybe, or probably a fastener, bolt, screw, and out. In this case, okay, I just put connectors to make sure that to imitate real life conditions. Setting up my mesh. Okay, I often say this: smaller mesh creates more accurate result, but also requires more time. Okay, but here let's just run this so-called mesh settings, and let me just save the file in Inventor. So I'm saving the file, so it's already have the result, and then now it's processing the studies. So in Inventor Nastran now is processing the simulation studies, and the so-called studies has completed. So result is already there. Okay, so you can see the result. So this is from the file that we bring in from SolidWorks. You can see and look at the result straight away. So it does not really necessary that you just need Inventor files. It can also work with other file formats. So no issue there. Okay, so now what happens is, since this is so-called In-CAD technologies, right? So basically the associativity and the relationship is maintained. Now I go back to SolidWorks, edit the parts, add some features, add some stuff, and then save it. Go back to Inventor, and I just simply update. I get the latest update from the SolidWorks model. And then I just rerun my mesh, rerun my studies to get the new result. So obviously, in this case, it will improve the result a little bit, because this is considered as adding a support to strengthen the components. So basically, you don't have to redo applying all the loads, applying all the constraint again, all the connectors. You don't need to do that, because it still maintains the same setting as before. We just need to click update, basically. So we get a new result, okay, from the updated models. So imagine that now you can so-called collaborate better with another third party who is using different application, a different software. Okay, so that's on In-CAD technologies, which helps a lot in this interoperability status cases. Okay, so let's look at the next slide. Before that, let me check if I have any questions. So I don't see any question yet. Okay, so if you have any question, you can just type in at the Q&A box. So we'll respond accordingly. Okay, so when we talk about Nastran, right? So here is some key points that we can so-called like remember. Okay, so Inventor Nastran for engineers. So ATTN. So this is like for example, like a keyword that I always remember. So Nastran benefits. Just remember that it can do assemblies. Okay, all the bolted connections, sliding interface, contact friction, you can simulate or you can run simulation on that conditions. So if you require time-based analysis, transient dynamic loads, vibration, fatigue, this is where Nastran comes in as well. Temperature, so consider the effects of heat, or you can solve for temperature, heat loads, thermal expansion, and also thermal stresses. So this is also where you require Nastran. Okay, so and nonlinear analysis that goes beyond normal or standard linear analysis like displacement, large displacement effect, buckling especially. So this requires nonlinear stress studies, which Nastran can help to cover you. If you already have inventor profession, this is what separates it from normal inventor simulation and inventor Nastrans in product design and manufacturing collections. Okay, and then just a quick check. So for verification manual, so they basically they are sharing with you guys. So all the users, so how the calculation is made. So what is that the format of the or formula used to calculate is all publicly shared on Inventor Nastran interface. It can easily access from Nastran tab as well. Okay, all right. So when we do studies or simulation studies, there are multiple ways of doing simulation studies where there are multiple formulas, methods to do the calculations. Okay, so there are even analysts who is so-called master or experience in calculations of certain part validations and so on. Okay, so in this case, let's just look at FEA or Finite Element Analysis method. So basically, to put it in simpler words, FEA is a method of solving problems of engineering and mathematical physics by let's say by so-called from big components or big area, big profiles, separated it into a smaller area, smaller files, and calculation is made into the smaller area. So model body is divided into smaller equivalent systems, and then can be run or calculated accordingly based on the surface data. So in this case, so here is types of finite elements that I mean the elements of FEA. So it can be 2D line elements, 2D plane elements, and 3D elements. So basically, if you notice, everything consists of triangles, shapes. Okay, because if you notice, even meshes is triangle shapes. So basically, the calculation is done with meshes, and also this FEA is calculation done with the shapes of a triangle. Okay, common FEA application. So this is pretty much well known to everybody, but here is a quick sharing. So mechanical, aerospace, civil, automotive, engineering. This is the most common one. Okay, and then I can say the most needed one. Okay, structural analysis for static and linear and also non-linear, fluid flow, heat transfer, electromagnetic fields, acoustic biomechanics, and also soil mechanics. Oops. Okay, so why do we need FEA? Or basically, why do we need to validate our products? Okay, so predict the performance of our products for planned use, I mean for future use, predict the potential failure with predictable abuse. I mean, we need to make sure that when we design products, we need to make sure that we have a certain target or expectation how the product will perform. So we can use simulations, studies to so-called predict how much can a part or a components be stressed in daily usage. So evaluate and correct observed failure so that we can check for potential failure before we mass produce, which will save a lot of cost, improve performance and safety, of course, improve cost and weight. So imagine a part that is over designed. Okay, so when you run the studies, you know that this part is over designed. So maybe we can reduce materials or reduce some weight. So basically, but while maintaining the safety factor of a component. So imagine from one component, you can save some material. Imagine if you mass produce the things. So you'll be saving a lot. Okay, develop new and innovative concept, of course, by doing simulations. You will open up to more ideas. You will see in the studies or in the result, right, which area or which so-called area is most affected. So you can probably reverse engineering from there to develop new and improved products. Okay, and of course, modeling decision should be driven by goals. So every time we do product design, surely an engineer or a designer will have a goals, right? For example, let's just do something very simple, things like a table. If you are in a furniture company, so you are designing a table, so of course you need to know, or you need to so-called have a target. How much weight can that table stand? Okay, probably like 200 kilos, 300 kilos. So we at the moment we can just say and predict from experience, but to get a theoretical result or data to support is a separate matter, which you need simulation for product validation. Okay, all right. So next, let's look at the workflow. Okay, the way the methods to operate Nastran. I can say it probably is almost similar to any other application as well. Okay, so let's look at the so-called the first idea. So the idea, we haven't gone into details yet. Basically, there are only 1, 2, 3, 4, 5 steps. Of course, create geometry. You need to create geometry. You can't simulate anything without a 3D models, and then you need to assign a proper material properties, a material that is similar to the real life products. Okay, you don't want to test something that is different material from something that you will mass produce. Create mesh. Okay, mesh settings is also important. Okay, apply loads and constraints. So this is also very important because loads and constraint comes from the engineer, so the user or the operator who run this analysis. So basically, getting loads and constraint, loads information especially, is very, very critical. Okay, and then specify constraint. So as a designer or as the product engineer, you know where is the constraint of your products. So where does the constraint area is? So is the leg, or is it the base, and so on. So an engineer or designer of the product should know. Okay, and then of course at the end is review the result. Okay, so to review the result also, there are so-called multiple way to so-called determine whether how the product is safe or not to use, whether there's any deformation or not. So there are some ways to read the result. Okay, so in a case where when we review the result and then we think, okay, as an engineer, so we think that, oh, probably I can try to maybe add some support to my parts, or maybe I can remove some materials. Since the product is very strong, maybe we can remove a material, make it lighter a little bit. So from that result, you can go back to the geometry creation or edit the geometry. And then what's good, since it's integrated within Inventor, right? So basically, you just make the edits and just update the so-called mesh and also the studies, and it will recalculate again. So you can do this multiple times. You can also combine multiple studies together. We call it subcase. So in case, for example, you want to test thermal and also stress. So you can create thermal stress first, and then you can create a thermal first, and then you can create stress after that. So you can run the simulation together. So you can get the result for both studies. Okay, so determine if design changes are required. This also is reduce chances of failure. Okay, I've mentioned failure a few times already. To improve product performance, and as so-called as a manufacturer, optimize for cost is very, very important. Okay, all right. So a little bit more details. Okay, basically it's almost similar with the previous slide. So basically, preparing geometries, choosing the type of analysis of physics to be used. Okay, material properties that we want to use. isotropic, anisotropic, and nonlinear, and so on. So, and then the idealizations of the studies. So it could be beam elements, it could be shell elements, or it could be just 3D solids. Okay, creating meshes and also mesh settings. Number 6, define boundary conditions. Okay, this one requires an engineer or the product owner to really understand how their product performs in real life. Okay, how they want their product to perform and how their product perform. Okay, basically, what is the load they want to study? They want to test where is the constraint of their products, rigid elements, and also the context. So if this product requires any context, things like probably like bolts and nuts. Okay, so that is considered as contact as well, fasteners. So you need to get accurate result, you need to specify where is the context. Okay, run analysis and view the results. Okay, so basically this is it, the flow. Okay, a little bit of overview of Nastran in CAD model 3. Oh, I have an extra E there, no problem. Okay, so basically if you are an existing Inventor user or any other applications user, so you should be familiar with the browser on your left hand side where it stores all your history. Okay, all your design history. So basically in here, the top portion, this is after we change from design to so-called analysis, or to Nastran in Inventor. Okay, basically just change the tab and activate Nastran. Okay, so the top portion is for analysis. Okay, all the analysis information, and the bottom portion is for model sections, information about models, to include certain components into the simulation and so on. Okay, so far any questions? Let me see the Q&A. So it looks okay.
Syed, I think you can go ahead. I don't see any question at this moment.
Yeah. Okay, yep. Thank you for the updates. Okay, so I am going to show you a little bit of demos with linear static stress with bolted connection assembly. So this is assembly, yeah. Okay, so this is for assembly concept. Okay, so linear static stress with bolted connection. So bolted connection, if something on the chat box. Okay, no. All right. So basically, when we talk about assembly or linear static stress with bolted connections, or so basically what we require is of course the assembly. Okay, so there are two conditions where we create or model our own bolted connection with bolt, screw, and nuts. Okay, there, or we can specify it from our Nastran. So from Nastran, we can specify that that hole have bolted connections with what size, what type, and so on. Okay, so in this case, here is the so-called conditions that I'm going to run. So I will have a surface contact of this so-called assembly. Okay, the wall is fixed, of course, and then we're going to put in a stress of 5,000 Newton to this U-shaped steel. Okay, and then we have some welding here, so we can test it on this welding strength as well. Okay, and then for the top portion, we're going to use bolted connections. Okay, all right, so the final result should look something like that. Okay, but let's just see how do we do this. So when we create linear stress, so the first thing, okay, the first thing on engineers' mind, or anyone who run the analysis, right? So it's usually the engineers. The target is trying to get the smallest displacement as possible. Okay, so smaller displacement, or we can let's rephrase it, smaller deformations or smaller displacement is pretty much similar. Okay, so let me just show you guys. Introduction on linear static stress with bolted assembly within Nastran. Okay, so let's look at so what to expect. So So we're going to use this simple assembly just to create a situation where we will see that we have bolted connection, welding, okay? So, and all the constraint with 5,000 Newton, okay? And then here is the end result, okay? All right, so let me just go to my Inventor Nastran. Okay, so this is your typical Inventor interface. So I believe you all are very familiar with this as well. Okay, so to use Nastran, so you first of all you need to have a Nastran license. Okay, so let's say your customer is buying or you have PDMC, so you should have Nastran license together. But the installer is separate, so you need to install Inventor first and install Nastran. All right. So and then where do you get this Nastran environment? So basically it's under environment tab, and you can see here on the begin panel here, you will see Autodesk Inventor Nastrans alongside with all the Inventor environments that available, like cable harness, tube and pipe, stress analysis, and so on. Okay, right. So let's just simply keep to Inventor Nastran. So it will load Nastran here. So as you can see, we have a Nastran tab. So this is all the things related to Nastran. Okay, so here, so let's see. So how do we start with Nastran? Okay, so first of all, of course, everything is about settings and everything. Right, so let's say we start a new analysis. So with this one, so you can see that here, okay, you can see that we have to put in all the details about our analysis first. So basically, what's the name of our analysis? So what's the type of analysis that we are going to do? So this is all the type of analysis that's available in Nastran. So you can see all the lists here. Okay, right. So but for this exercise, I will just use linear static. Okay, and then what about output control? So what is this output control? So basically, these output controls determine what type of result that can be viewed. Okay, so this need to be chosen before you run the analysis in Nastran. Okay, so all the output results are basically at the nodes. So there is only one result at a node. Okay, so let's look at some of these points. So for this exercise, I'm going to use displacement, which is the output will show displacement result. So if displacement is not an output, so the deform shape cannot be shown. So you cannot see the deformation of shapes, but whenever you click on the animation. Okay, and then we have applied loads. Okay, and then for this case, I'm using SPC, which is a single point constraint. All right. So, and then the rest is options, contact data. So basically, when you start the analysis, so Nastran will give you one default setting, which is everything is set to bonded and 0.1 tolerances. So which the thing you can adjust later on. Okay, and most important thing is the unit. So you can see here that we have unit system set to CAD model. Basically, it follow the CAD model. Okay, and all the corresponding units is set to whichever suits our needs at that time. Okay, so it's just okay here. Let me just okay. So I already set the things. Okay, so from here, so what I'll do is, so I'll usually I'll start with my left hand side. So like just now I start with new, and then I'll go to the right hand side. So for example, let's say materials here. So first of all, in case by right, you should have applied materials to your parts and assembly, right? So in case you did not, okay, so you can assign the material later. So in this case, we have a material browser here. Okay, so let's say I can set on what is the material that I want to use during this simulations. So let me just close this first. So if I did not assign materials, so later on, okay, later on, I'll need to whenever I want to use idealization here, so this is all the materials that are available to me. Okay, and then I need to reassign again. Okay, so which I like to do it earlier. So in case I do it here, it's already on this tab. So that's why I say I like to start from left hand side here and go to the right. So let's say here I just select one material. Let me just choose one steel here. Okay, so this is steel material. Okay, the tree. Okay, so once I assign steel, you can see that this is steel has been shown here on the materials. So you can see here on our browser here, this is all the information, all the notes about loads, constraint, solids. Okay, so now after I assign the steel here, so whenever I go to idealization, so I can just add the information. So I can, in a simple term, I can group a few components together. Okay, so let me just go. I already added my solid here. So let's say, let me just edit my solid. So I have solid one. So of course, solid elements. Okay, what about material? So I need to assign. So what material do I want to use for my solid one here? So in this case, I want to use steel. Okay, so I can assign what color do I want. So let's say I change this one to orange. So easier for me to differentiate later on. Okay, so I already assigned material. So next I want to assign the geometry. So what geometry is using our steel here? So let me just click associated geometry, and I need to click on my window here. So in this case, I'll just click on the angle, gusset, the welding, okay, and together with our friend here, the U rod. Okay, so just click them together. So basically all this will be using steel. So just to make it simple, I'll assign everything to the same material. Okay, so now as you can see on my browser on the left hand side, solid one already changed to orange color. Okay, and then as you can see here, I already assigned as what I did earlier. So let's just proceed to the solid 2. For solid 2, it is this concrete over here. So I want to assign this concrete here. So let's say if I click this concrete, okay, so and then I can either, if you can see it here, so you can turn on or turn off the visibility or even exclude it from analysis. So in this case, I want it to be inside this analysis. So let me just go to solid 2. Okay, again, and then material, of course, I have concrete. Okay, so geometry, I can just click on my concrete here. Okay, so but for this concrete is actually already been assigned earlier on. So if I can see here under my modeling browser, I can see it that this has been assigned to concrete in the design environments, but not the let's say let's look at this angle here. If you go to properties and check, okay, so here is still using generic, which means it's still not assigned. So if you already assign it earlier on during the modeling stage, so it will be auto-populate here accordingly. Okay, so what we're doing here, we just override the material. Okay, all right, so that's done. Okay, so now after the idealization, so I need to create some connectors just to so-called to show that in real life that there is something that hold this angle with the concrete, right? Basically, there will be some fasteners, right? Okay, so what I'll do is I will so-called add a connector. Okay, so I'll add connector. All right, so connector 1. So I can choose the type of connector that I want to use. So in this case, I'm going to use bolt. Okay. And then I'm going to use a cap screw. Okay, bolt diameter. Let's say I put 16. Okay, the head washer height is 2, and the length. Okay, the length of the bolt is 30. Okay, so let's just assign it to 30. Okay, so what about the materials? So I can assign the materials here. So as you can see, I can use the same steel, or I can load another materials and assign later on. Okay, in this case, I just put it to steel first. Okay, and then let's just put in some preloads. Okay, 300 Newton for preloads. Okay, so now, so we need to place these so-called connectors, which is our cap screw connectors. So we want to place it here. So this is bolt one. Okay, here they ask us about bearing surface H for bolt head. So where do we want to place our bolt head? Okay, let me just zoom in here. So I want the bolt head to be here. Okay, and then about the surface for threaded region. So it should be here. All right, and then you get that preview there. So it looks good. So everything looks good. So let me just create another one. Okay. So now let me close that. Okay, so let me just go back to my browser and check my connectors. So this is connectors one. So material is okay. So I want to edit my connectors. Okay, let me just add another connectors. Okay, so similar like before. Or I can just copy this. Okay, never mind. I'll just create a new one. So connected to, let's say, bolt. Okay, cap screw, 16, 2, and 30, 300 preload. Okay, then material we use steel, so same thing. Okay, so this face, okay, and then this one. So get the preview, everything looks okay. Let me just click OK. Okay, so everything looks good. Okay, so far so good. So next one, so what do we need to do? Okay, so we're not going to use any offset surfaces or structural members in here. So next we're going to do some constraint or context first. Okay, let's say if I do some constraints, so I need to make sure that this fix the back here. Okay, I want it to be fixed. Okay, so here is how do we set the display in case we want to see. Okay, like previously, if I did not click the preview button, I will not aware that I have actually put on some constraint here, right? So I always like to make it show so I can know that it's there. Okay, let me just put, okay, so that's the constraint. Okay, now let's do some context. So in this case, we just do some auto context. Okay, so it will run for a few seconds, and then you can see that under our context, so it should be here. Okay, surface context. Okay, see, this is all the auto context that has been assigned. As you can see here, since we have put on a proper naming for the files, right? So you can see, so this is the first contact, which is for gusset and well. Okay, so it's this one. So let's say gusset and well. Okay, maybe this one is angles and well. Okay, so in this case, so what I want to do is I want to suppress the angle and gusset context because we want it to rely on the well, right? Okay, so let's just look for angles and gusset here. Okay, we can suppress this. Okay, and then one more angle and gusset. Okay, and also suppress this. Okay, so after I suppress these two, okay, I need to double confirm and double check my angle. Okay, this part here and this concrete. Okay, so this contact. So what are the contact used for? These two components. So angle and concrete. So this one. Okay, so right now, let me just right click and edit so I can make some changes here. Now at this moment it is bonded, so I want to change the type to sliding, no separation, so it can slide. Okay, just okay. All right, so once I done that load, so what else is I need to, there's some very important thing that we miss here is the loads. Okay, so after constraints, usually we need to assign loads, right? So but I missed that just now, so let me just click load. So in case I've forgotten to apply loads and then I already do some meshing and then run, it will prompt up an error that I missed something. Okay, it will prompt up an error saying that, oh, you forgot to assign loads. So let me just do it since I noticed that I've forgotten to do it earlier. Okay, so for loads, so what do I do? Let me just use load force. I want it to be here. Okay, let me just turn on the preview so I can see. Okay, and then let's say I put 5,000. Okay, then I click at the other tabs and I can see preview. So now it's going upward, which is not correct. But since we already turn on the preview, we know that this is going the wrong way. So I can just put a negative there. Okay, and then it will show, oh, it's going down. So now it's correct. So let me just click OK now. Okay, so now constraint done, loads done, context done. So the next thing will be the mesh setting. So this is also very important, especially for simulations, because the more accurate or smaller your mesh, I mean your result will be more accurate. Okay, but it also will consume a lot more time. So let's just go to our mesh panel here. Let me just do here, mesh table. So in here you can detect that all the components are meshing. So we can assign every component have different mesh size. Okay, so it's not one for all. So we can actually assign. Okay, so in this case, let's say I want to on this right hand side, you can see that there's a check mark here, right? So here, if I check all, so if I change one, everything will change accordingly. So in this case, let me put 4. So everything changed to 4 because I checked this. But later, if I change this again, so let's say I want to change this to 2, it will change into 2. So which is not ideal every time. So after I done once, okay, let me clear it. Okay, and then I put 2 and here, and then sorry, for concrete, not 2, for concrete, let me just put 15 because it's not critical, it's behind there. Okay, and then for well, so well, let me change the size to 2, so smaller. So well, we have smaller size mesh. So everything looks good. So everything, let me just click OK. Okay, so mesh is there. So let me just click generate mesh now. So we'll see how the mesh looks like. Okay, so remember that I put 15 for concrete. So you can see that the concrete here is bigger. Okay, and then 2 at the well. So you can see at the well there is smaller. So the rest is 4. All right. So now, after checking, so everything is okay. Looks okay now. All right. So the next step will be to run our simulation. So let me just click run. Okay. So it will run. Okay. Give it a few seconds. Depending on the simulation. So if it's complicated, the size is big, there are many components, it will take longer time. Okay, but of course you can play around with the mesh size. So for draft purpose, or maybe for the first stage, you can put bigger mesh just to indicate that everything is working. Okay, all right. So now this is done. I think it's almost done. Okay. Nastran solution complete. So let's click OK. So let's look at the result. Okay, so this is, let me just close this one. Okay, so by default, this is the type of result that will show us. So von Mises stress. So here I can see that I have 198.3, but you need to remember so that this view is probably has been adjusted. So let me just go to options under result here. So we can see that deform options. So like this one is already been set to 10%. So let me just set it to actual. So you can see it in actual condition. So it's not exaggerated like this. Okay, so actual, so looks okay. If we set it to actual, okay, contour options, so everything looks okay. Animation, visibility, okay. So let me just click OK for now. Okay, so here we already able to see the result of von Mises stress. So how do we know that this is workable, that this is strong enough? Okay, so first of all, we need to know that we are doing this based on yield strength. So we need to know this material. Earlier on, we assign it to steel, right? So we need to check what's the yield strength of a steel. Okay, so how do we check that? So usually people just go Google, or in factory, usually they'll have their own material catalog so they can refer. Okay, so but in Inventor, since we assign it to our Autodesk material, so let's just look at our steel just now. Okay, let's go to our material properties, steel. So just now I was using this one, this steel. Okay, let's look at the steel properties. So let's look at their physical properties. In here, you can see under strength, it is showing the yield strength is 207 megapascal, while on our design here is 198.3. So by right, it should survive. So it should be okay. Okay, just enough. Okay, let's look at our displacement and then see whether if there's any big displacement happen for our part here. We go to displacement. Okay. Okay, as for displacement, you can see the total displacement here is 0.1175 mm, which is very minimal, you can say. All right, so it should be able to survive the 5,000 Newton loads given to it. Okay, so if you add more loads, I mean you will get a different result. Okay, so let's say if you want to let's just go to option here, and then maybe I'll go to part view. Okay, so I want to look at part view. Okay, and then I click on the weld. Okay, I click on the weld. Okay, so now I can check the weld. Okay, let me just do that again. Okay, result. Let's look at von Mises stress. Wonder what happened just now. Okay, von Mises. Okay, so by going to options and then part view, we can see the welding result. Okay, whether in this case it should be stress. Okay, set to stress, and then our solid von Mises stress. Okay. All right. So let it loads. Okay. So now this is just to show you that you can also view the result part by part. Okay, so everything is under the result option, and of course, as you know, we can generate a report from this. Okay, so by you can go to I like to go here on the browser, and then generate report. So, but of course, before that, we need to enable these two settings. So let me just click yes now here. Okay. And then it will generate the, I need to regenerate again. Generate the reports. Okay. So from there, you can generate the reports, and of course, this is the report wizard that you need to fill up the information. So who's the author? So what's the subject? What's this simulations prepared for? Who is it prepared for? So you can put in your assumptions earlier. Okay. Okay. So so whenever you finish, you need to save it. So you can save it to your locations. Okay, and then you can view the result later. So it's in HTML format. So let me just, maybe I can open this one. Okay, so this is the one that's already been run earlier. Okay, so this is the template of the so-called report. Okay. All right, so everything is here. Subcase 1. So as for displacement, you can see the displacement. Okay, so I think that's all from me. So now, okay, all right. So that's all on the so-called demo or hands-on. Okay, so I'm at the end of the presentation. So next, Marcus, you there?
Okay, yeah, I'm here. Thanks, Syed, for the quick overview and short presentation of the Nastran In-CAD capability. Once again, the good thing about Nastran In-CAD is whatever material being assigned in the modeling, automatically you're put over to Nastran In-CAD. But actually, Syed and showcase is that due to some reason, maybe should you want to change any of the material, you can still override the material property from aluminum to a steel or steel to concrete, so on and so forth. So, and of course, within this such a short time, 1 hour, we won't be able to showcase the full capability of Nastran In-CAD. And of course, Nastran In-CAD actually allows you not only from static, vibration, linear, non-linear, drop test, heat transfer, so on and so forth. So we only cover part of the analysis studies itself. So if you want to find out more, of course, we can do a one-to-one meeting or presentation to you once again. So, and before we end the webinar, there will be some it's time for Q&A. So meanwhile, so how do we start? Once again, we are the authorized training center for product design and advanced material analysis. So we cover trainings from Nastran In-CAD, Inventor to MoFlow, so on and so forth. So we also cover some advanced material courses, and of course we do customize your trainings based on your workflow and your requirement. So, and other services, and not only that, we do sell the solution, we also provide, due to some reason, maybe you don't want to, maybe you're not ready to embark to this solution or purchase and you use it. We do also provide some services, ad hoc services, should you require us to provide FEA study, structural and computational fluid dynamic, CFD, and so on and so forth. So in a nutshell, not only we sell, we also provide services, trainings, and it's end-to-end solutions. So let me just wait for a few more minutes for any Q&A. So meanwhile, Syed, you can also check whether is there any questions inside the chat.
Sorry. So there are not really a question. The content is blur, can't see the content clearly. So Marcus, your side, is it clear?
Yeah. So I think the video was actually quite clear. I thought it's my bandwidth, so I'm so sure is it also same to everyone. So I didn't really stop you. Yeah.
Okay, never mind. But since the recording is recorded, right, and then it will be shared. So I also will give a link to Marcus for that video. So I did that. I record that myself. I'll give you the link in case needed to share.
Will do. Yeah. That's other than this session, we also at the end of this session we actually send all the recorded session to all the participants over here. Okay, so let me just wait for a while.
Okay, one question: basic stress analysis in Inventor is unable to perform on structure member with thin thickness. Is it possible now in Nastran? Yes. For structural is for standard Inventor Pro simulations, right? So for thin thickness, especially for structure members, usually it's either have a little bit of issue or not really an issue. It can't perform too thin or of simulation, but it's now possible to be solved within Nastran.
Yeah, just to add on, if let's just say you are using just the pure Inventor Professional, so what I actually have presented earlier is actually an add-on analysis capability, which is only available in the PDMC collections, which is Nastran In-CAD. So if you are just using Inventor Professional, you won't be able to perform anything more than the static structure and vibration and the thickness itself. Correct me if I'm wrong, aside. Yeah.
Yeah, correct.
Yeah. Okay. So like what actually Syed actually presented at the beginning, so you can actually do much more than what Inventor Professional can actually do in terms of the analysis. Once again, it's more like more than what you can do. You can go up to linear, non-linear, static, vibration, and heat transfer, and drop test, so on and so forth.
Okay, there's no more questions. So I think we overshot the time by a little bit. Sorry about that.
No
but
problem.
so,
Would there be another slide? Is there a last slide? Sorry.
Oh,
No, is it?
no,
more
this is the last one.
Okay. Yeah. So once again, maybe you just bring back to the main page on this my that actually show our company profile and my
Oh,
email.
okay.
Yeah. So that actually, if let's say they have any questions, you can. Yeah. One more.
This,
Yeah. Okay. Yeah. So
this.
once again, no, yeah, correct, this one. So once again, thanks for staying tuned and overrun by a little bit. So and thanks everyone for staying back for the additional 10 minutes. So if you want to find out more, you can either drop me an email. Okay, and this is my email, or you can also drop another email to my my colleague actually Ichao. And alternatively, you can click on the link, or you can go to this website to find out more on the services and the training that we will provide to customers. Okay, just wait for 1-2 minutes before we end the session. So yeah, sorry. I think there's a Q&A, or rather feedback will be sent to the customer here. So we do appreciate you can just do a fill out on the feedback form so that we can improve on our next webinar. Or if you want to see much more than what we have presented, do feel free to drop in inside the information. Yeah, so sorry, that's breaking. So just help me to input all the informations accordingly. So we will actually address those inquiry or those additional information you need. We will get back to you all accordingly. Thanks.